Okay, so hope everyone's going well. Now today we're going to be looking at a few different transformations and general ways we can change our general function of we're just going to call it the generic function f of x and the different ways that we can move it around. Now this is a pretty important topic. There will absolutely be questions that involve these kinds of things in the exam. And they're really universally useful as well because it sort of tells you how we can shift one of our functions to the left or right, or what actually happens when we start changing around with with what's going on with it. So I'm just going to pull that up. So I would strongly recommend that you make sure that in your own notes you have your own copy of what I'm about to show you. If you do not have your own copy of what I'm about to show you, you will be severely disadvantaged, including using the correct terminology for what I'm going on with. So just make sure that you understand what's going on with it, and we can make sure we're all on the same page with it. So we're looking at transformations today, and we had a bit of a look at that in a previous lesson that I had recorded, but now we're going to be looking at it in a bit more detail and making sure that we use the correct terminology for everything that we're doing. So we've got here what I'm going to call a general function, which is f of x. So this is obvious. This is the function that we've got here. It's the blue line. Now, I've got as an example f of x equals x cubed. Now, this is obviously not f of x equals x cubed. This is not the function of x cubed. It's a cubic, but it's a different kind of cubic than x cubed. But this is going to be a really good illustration of what our various things look like. But I'll be using this example of f of x equals x cubed to show us basically what we can expect it to look like when we actually do those kinds of transformations. So let's have a look. So there are a few different things that we can do with our general function, and generally when we're transforming it, we're either doing something on the outside of the brackets or on the inside of the brackets. And I'll show us what that means. So basically, if we had adding outside the brackets, that basically means that we would have f of x plus a. So we take our function, we add a to it. And that would look like, if we had our x cubed, it would look like x cubed plus a. Now we should be fairly familiar with this one. This basically just means we're moving it up by an amount of a. So basically, we move it up by a certain amount, and however much we add is however much we move it up. And that's what it would look like in each of these situations. Then we've got subtracting. This shouldn't be too hard. F of x minus b, and I'm going to use all the letters of the alphabet as we go through, and that might look in an actual function as x cubed minus b, like that. And that would basically be a shift downward of b, depending on what b ended up being. So these are all both called vertical translations. One is a vertical translation up and a vertical translation down. So that's how you can refer to them. These are just vertical translations. So when you're asked to describe what kind of transformation it's undergone a vertical translation when you're adding numbers outside of the brackets. And now we've got this idea of adding inside the brackets. Now we would have seen this one before as well. And this would be, for example, f of x plus c. And this is when we'd have, for example, x plus c. Let's get that lined up properly. There we are. X plus c all cubed. And we should recognize this one as being when we shift it to the left by c. So now one of the running themes in inside brackets compared to outside brackets, the inside bracket will do the opposite of what you expect it to do almost every single time. So whenever you've got something inside the brackets, it'll do the opposite of what you expect it to do. So for example here, the positive x direction is off this way, but when we add a number in the brackets, we actually go in the negative x direction. So it does kind of do the opposite. You can think of it as being something that is impeding what x wants to do. So basically, or helping x along with what it wants to do. So basically, it has the opposite effect. And that's something we're just going to need to be used to. And you should be used to that if you're used to, say, when we do x minus 2, x plus 3 as a function, this has the solutions of x equals 2 and, or this equals 0. This has a solution of x equals 2 or x equals negative 3. It's the opposite of what the number is inside there. So, but with brackets in general, we will find them doing the opposite of what we expect it to be. So, that's inside brackets. And obviously, this is the one we're more familiar with. When we do a subtraction, f of x take d, and that would look like x take d, all to the power of 3. That's when we move it to the right by d. So it's being moved to the right by d. Again, it's the opposite of what we expect. We're subtracting, but we're moving to the right, which is the positive direction. So that's just something to be aware of with those. So these are our 4 different translations, up, down, left, and right. And we should be also familiar with this, with the turning point form of the, where was it? The turning point form of our quadratic, x take p squared plus q. That basically takes our basic formula of x squared, shifts it to the right by p spots, and shifts it up by q spots to give a turning point of p comma q. So that was our turning point form of our quadratic, and that's what's actually being done here. It's being translated to the right by subtracting something inside the brackets, and then it's being translated up by adding something. So yeah, it's translated right by subtracting inside and translated up by adding outside the brackets. So that's something that we start to see. That's something where we can tie it back to stuff we've been looking at. Okay, so let's have a look a bit further down. Now we've got multiplying and dividing. Now I've been a bit cheeky about what I'm calling multiplying and dividing. Basically, if we're multiplying by a number greater than 1, then I'm calling it multiplying. If we're multiplying by a number less than 1, I'm calling it dividing, or dividing by, basically we're dividing by a number greater than 1. So basically, if we're multiplying, or whatever number we multiply it with, if it's greater than 1, we do this top one, and if it's less than 1, we do the bottom one. So anyway, let's have a look at here. So when we multiply outside the brackets, that's going to look like e f of x, or it's going to look like e x cubed, like that. So if we take it back to our x cubed, and what that does is it boosts it up. So basically, it will be multiplied, so multiplied by e. So whatever this point happens to be on there, we multiply it by e to get that point up there. And the same down here. And we call this a vertical dilation, and it's got a factor of e. So remember, these terms are very important. It's a vertical or horizontal translation, or it's a vertical or horizontal dilation. So this is a vertical dilation. I'll go down to the vertical dilation when we're dividing. So that would look like f of x over, now I'm choosing f again here. Don't get confused, this f here is not the same f as that down there. This is f of x. This is just a divisor of f. So we're dividing by f. That means that whatever our thing is there, it is divided by f in there to get to that one compared to what it was previously. So I'll go back to green there. So f of x divided by f, that would look like x cubed divided by f. And as you might expect, that just reduces it down so that it is not so vertical, or doesn't go up as high as it would previously. So that's an idea. This is our vertical dilation, and we say what our factor is, and basically that will be whatever our number that we're multiplying it is by. So we still call them both vertical dilations, and we just list the factor, and we list it in the form of, if we are looking at a f of x, we would say whatever that number a is. So if a happened to be 0.5 f of x, technically we've got a factor of 1 on 2, but we could say, oh yeah, technically we're dividing by 2 here, but we would just say a vertical dilation of 0.5 or 1/2. Anyway, horizontal dilation. Now this is the tough one. This is the one that is a bit more complex. You may not expect it to do what it does. So this is when we are inside the brackets, and this is a bit counterintuitive when we're looking at our typical cubic, but you can start to see it when you graph a bunch of different graphs. So f of gx would be what that is. We're multiplying inside the brackets, and that would look like g of x all cubed. So that's inside the brackets that we're doing that one. And what this does is something a bit counterintuitive. It doesn't actually move it any further up. It moves it in. So basically, it would do the distance horizontally will be divided by g. So if we, and that does a little bit different to what we expect it to be. What we can think of it is as this number here is helping x along. So x doesn't have to put in as much effort to go where it would be otherwise. So x only has to do this much effort. It only needs to put in half as much effort to get to this point than it did when it had to go all the way to that point over there, because it's got this little horizontal dilation factor helping it out. So that's one way we can think of it, but it's basically, this is a horizontal dilation. It squashes it in, and that is the trickiest one to get our heads around. These two, the horizontal dilations, are definitely the trickier ones to get our heads around. Then we've got another horizontal dilation. Basically, this is where we go out. Actually, let's get the right color. And we actually multiply by whatever our divisor would normally be. And the way we can think of that is it's got to put extra effort in. X has to put in extra effort to get to the spot where it normally got to before, because it's being divided by some kind of number. And that would look like f of x over h, or x on h all cubed. Now this one is a little bit counterintuitive, especially when we're looking at this, because we could use index laws to work out that, well, that's actually x cubed over h cubed. Isn't that the same as what we had over the left side? Isn't that the same as a vertical dilation with a factor of 1 on h cubed? And the answer is, yeah, it is. It is exactly that. Which is why x cubed isn't the best thing to use, and like this one likewise, if we used index laws, we could see that a horizontal dilation with a factor of g is exactly the same as a vertical dilation with a factor of g cubed, if we are dealing with the thing gx cubed. But if we've got different sort of things, then we end up seeing something a little bit different. But that's all much of a muchness. We don't really need to worry about that just at the moment. And that's why I drew these sort of more sort of curvy lines, so we could more easily see the horizontal dilation factors that we can't see if we're just modeling it on x cubed. So that's those ones. The last one, and remember these are called translations, dilations, vertical or horizontal for both ones. And then we've got what we do when we have a negative. So in this one, our negative would be f of, let's do that in green, negative f of x is what it would look like. So that would be negative x cubed. And what this does is it reflects it in the x-axis. So basically, every single point is shifted, or the blue line is shifted to the red line across every point. And that is our vertical reflection, or our reflection. So it moves vertically, it reflects in the x-axis. So if you called it a vertical reflection or a reflection in the x-axis, as if the x-axis was our mirror, then those are the two ways we can consider that one. And then we've got a horizontal reflection. This is when we've got the negative inside the bracket. So that will look like f of negative x, like that. And that will be negative x. There's the bell. Negative x all to the power of 3. Again, this one a horizontal reflection in the x cubed case is exactly the same as the vertical reflection there. But we just got to remember that we are dealing with something a little bit different. So this basically would flip with that one, and this would flip with that one. Our horizontal reflection is in the y-axis, so we've got our axis of symmetry across the vertical line instead. So now x cubed isn't the best example. I'm just using it for illustration, but it does show that sometimes we do have equivalent transformations. So there's an equivalent between this vertical reflection and this horizontal reflection when we're dealing with x cubed, because they would both end up being negative x to the power of 3 either way. But it doesn't always end up like that. So let's have a look at some of our questions. So we're having a look at exercise 7C. If you've got your textbooks, you can have a look at those. And we're just going to be practicing some of our vocabulary for these. And I would strongly encourage you to look through this entire chapter yourself. There's a lot of drawing graphs type exercises, and they're good practice. So and we want to use proper terminology. How can the graphs of these be obtained? By transforming the graph of y equals f of x. So have a look at these. You can pause the video and give these a shot before I go through the answers. But in this one here, y equals negative f of x. That is a reflection in the x-axis, or I would have called that a vertical reflection. So if we reflect it in the x-axis, then we would get that one there. This one here is a horizontal dilation by a factor of 4. Now what this would actually look like is, if I were to draw it, whatever my thing happened to be, this would be, if I had my line like this would actually squash it in a lot. Let's do it in blue so it matches our... So if I had this, a horizontal dilation by a factor of 4 actually squashes it in quite a lot, like that. That would really just sort of shove it in like that. But we call it a horizontal dilation by a factor of 4. And this one is a vertical dilation by a factor of 4. And just by comparison, whereas that one squashed it in like that, this one would stretch it up. So if I had now this is going to be difficult to draw, but I'll give it a shot. I do it like that, and this one would actually be more like going all the way down 4 times higher than the other one. So that's sort of going over my drawings a little bit, but you can get the idea. It stretches it vertically, whereas the horizontal dilation actually squashes it in. Okay, so that's those ones there. Now we're looking at what they end up looking like. So how are these graphs transformed from x squared plus 3x to negative x squared take 3x? That would be like everything's becoming negative. So that's going to be the same as above. It is a reflection in the x-axis. So we're looking here at how our function becomes, or what we do when we're actually dealing with something instead of just saying f of x. And so that is everything became negative. Here it's the same, but we've just tacked a -5 on the end. That's subtracting 5 in the brackets. So, or sorry, subtracting 5 outside of the brackets. So a translation down 5 is what I would need to say, or a vertical translation of -5, you could say if you really wanted to, but it's just been moved down 5. This one's a little bit tougher because we've got our x squared plus 3x, but here it's been divided by 4 and here it's been divided by 2. What's accounting for that? Why is it being divided by 4 for the first one and divided by 2 for the second one? So it's not just a matter of doing a vertical dilation, because if it was, these would both be being divided by the same number. What we've actually got is we've got x over 2 all squared plus 3 of x over 2. So this is where we are actually modifying it inside the brackets, and recognizing this is what this question's all about. Squaring this, that would give us x squared on 4 plus 3x on 2, pretty much matching what we've got at the top. So what we end up here is with it is a horizontal dilation with a factor of a half. So that's what we would call that one. And so that's a horizontal, not a vertical, because it's being done inside the brackets like we see there. So that would be modifying that inside the brackets. If this was x squared over 2, it would be a vertical dilation by a factor of a half. So we'd see that differently there. So now how are these graphs obtained? By transforming, we've now got y equals x squared. So this one is quite simply, now this is inside the brackets, we've got to remember it's being translated to the right, not the left. So being translated right by 3. This one here is a vertical dilation. Factor 3. Or, as a matter of fact, we could also consider it to be a horizontal dilation with a factor of root 3. And I'll leave you to think about why it also counts as a horizontal dilation with a factor of root 3. It may become obvious when I go on to this next one. This one is a horizontal dilation with a factor of 3. Or we could also consider it a vertical dilation with a factor of 9. And again, you can have a bit of a think about why that might be the case. So both of these, by the way, are valid answers. Both the vertical dilation with a factor 3 or a horizontal with root 3, and this there, those are both valid answers for each of those questions, though I think they're looking for the first one more than they are the second one. It's just that technically it's also that with this particular equation. But we couldn't convert between vertical and horizontal with this particular equation because we didn't have the same sort of comparison that we were able to get. Okay, so I've skipped a few questions here because they require a lot of graph drawing, and I really just wanted to, I don't want to waste everyone's time by drawing a lot of graphs. You're welcome to do that yourselves, and I encourage you to do it just to practice these. So we've got a graph. This is a piecewise defined function. It's not your typical graph. It just goes up and down and things like that. And what we want to do is we want to try to match up this graph, and I'll just zoom out a little bit. we want to try and match up this graph with a bunch of different graphs that I've got down here. And there we go, so we can see the whole thing. And what I want to do is try and work out which one matches up to which one. So I'd like you to give this a shot before just looking at the answers, and then I'm going to go through it. So pause it, have a look. I will, let's see. So if I scroll down just a little bit more, you should be able to see the whole thing. There we go, that's the whole thing. So let's have a look here. So we'll look at our first one. This one here is quite straightforward. It is half of this. It is a vertical dilation with a factor of a half. So this one up here, A, is quite straightforwardly going to be Y. Oh, it's not going to be that one there. That's the one where it's inside. It's going to be outside the brackets because it's being squashed down. So everything vertical is outside the brackets. Everything horizontal is inside the brackets. So that's vertical. Yep. So that's all good. Let's have a look at this next one. This one here looks like the whole thing has been shifted to the right by 2 because this point here is at 4, whereas this one's at 2. So it's being shifted to the right by 2. If it's being shifted to the right, that means we are subtracting 2 inside the brackets. So that will end up being that one there. Again, all vertical is outside the brackets, all horizontal is inside the brackets. So let's have a look at this next one. This one, has it just been shifted down to? Yep, looks like all that's happened is it's been shifted down to. So that's going to be subtract 2 outside the brackets. Pretty straightforward. Let's clean that up. There we go. Subtracting 2 outside the brackets. We'll look at the next one. What's happening here? So this one looks like it's been squished in. It's gone, so we can often compare our points. So this point here is at 1, negative 2, whereas the equivalent one is here is at 2, negative 2. This one looks like it's at negative a half and 4, whereas this one is 1 and 4. So this one is being actually multiplied. This is a horizontal dilation with a factor of 2, and this is the one that's a bit counterintuitive. This is where it's getting smaller, it's getting more squished in, but we're actually multiplying inside the brackets. If we were dividing inside the brackets, it would become more stretched out. Let's look at this next one. I'll start using some different colors. I'll go with some purple. So for E, I've got this one here. It looks exactly the same, but it's just been flipped upside down. So what's happening here? Flip it upside down, that is a vertical one, so that will end up being there. Vertical is always outside the brackets, horizontal is inside the brackets. And our last one, I'll do in orange. What's happening here? This one has actually been flipped horizontally, and you can sort of compare our highest point here to our highest point there. It's at 4, negative 1 here, it's at 4, 1 there. So it's being flipped horizontally. So this one here is actually our other one there with the negative x inside the brackets. And there we go. So now you've got your own textbooks. You should be able to do these ones. What we can do as well is this question 7 is quite a good one. I would strongly recommend you have a look. We've got this graph here. And so that's our graph of f of x. We want to find, for example, where does f of x minus 3 cut the x-axis? So that would shift the entire graph over by 3 spots. So that would end up looking like something like that. That's pretty good. I'm amazing. No, I'm less amazing. There we are. So that would shift our entire graph over by 3 spots. Where does that cut the x-axis? It cuts it at 1, 0. Remember, we're looking for coordinates here. Cuts it at 1, 0, 7, 0, and 10, 0. Just as an example. So I've just done that one as an example. We're going to find out where does this one cut the x-axis. What would it look like? For some of these, you may find that it doesn't change anything at all. And that's what we're just having a look at, just making sure we understand how that all works. Okay, so there we go. Give those a shot, and but I'll just end by having a look back at our transformations, and just remembering this. I can't say this enough. You must, I would very strongly recommend you have these notes, this page of information in your own notes. Copy it down. Do it as nicely with lots of different colors as you can, so you can understand what's going on with it, because this is a really important thing to have under your belt for exams. Okay, anyway, that's all for today. Have a great day, and I'll see you all tomorrow.